maybe stuff you've never studied before in your life, and certainly not in the depth that we're going to cover it. So it's just so many different and interesting topics and tools that it's just so exciting. It's just so exciting to get to do all this. Can you guys feel the excitement? Are you all already excited? All right, good. So let's see. You didn't make a name tent. You did take your student information sheet. You took all the other things on my desk. Did everyone get all that? All right. So good evening. Better yet, afternoon. It's just afternoon. It's not evening. Let's just talk for a little bit. So everyone, you can just put your pencils down and just kick back. I'm going to go through this pretty quickly, like I said, because all of you have already seen this presentation a semester ago or 2 semesters ago. So first of all, thanks for signing in on the attendance sheet. I'll have this attendance sheet right up here so you can sign in, hopefully always on the on-time side, not on the tardy side. Thank you for, no May 10th, and information sheet, I'll collect that on Thursday. Okay, so introduce myself a little, student introductions for the rest of you, syllabus information, course goals, and then we'll start working on our first chapter. So, you all know me. I really like math. This is a lot of fun. I'm looking forward to working with you. Please make sure you're checking your gateway emails all the time. Please email me anytime you'd like, and I'll respond to you on the same day. Okay, student introduction. I know I just went around and told everybody's names, but let's make sure that all of you have a chance to say your own name and what you're studying. So, what program are you hoping to complete? And we'll start with you. You don't have to stand. Just name really loud and then what program you're doing.
My name is Sadia. I'm going to be accounting.
Accounting. Okay, wonderful. Sadia. Say that again. No, Sadia. Say your name again, because I always say Sadia.
Sadia.
Sadia, that's what you said. Okay, that's what I thought. For a second, I thought you pronounced it differently. I was like, oh my gosh, I said it wrong all semester. Okay, and?
I'm Sarai.
Sarai.
Business communication.
Business communication. Okay, wonderful.
My name is Bata. I'm doing accounting.
Bata and accounting. Okay, super. So we have 2 accounting so far. Yes, sir?
My name is Diego. I'm doing accounting.
Okay, 1, 3 accounting and a business communication. So we said, yeah, okay. And then?
My name is David. I'm going for accounting.
Okay, accounting. Wow, a lot of accountants in here.
My name is Adon. I'm going for business management.
Business management. Okay, so accounting, business communication, business management.
And I'm Luis. Doing business marketing.
Business marketing. Okay, very nice.
I'm Simone, and I'm going for computer information systems and business.
Oh, interesting. So CIS and business. Okay, great, Simone. Thank you.
I'm Josué, and I'm going for computer information systems.
Okay, so CIS. So do you 2 have a lot of the same classes together? Oh, okay, very nice. All right.
It's an associates in business.
Oh, that's what it's called?
Mm-hmm.
Oh, okay. And then you'll transfer?
So
Right.
Okay, gotcha. So basically, for all of you, well, let me finish. Go ahead.
Hey, Cheryl. Business communication.
Okay, great. So are all of you finishing Gateway this semester? This is your last semester? Really? Is anyone still continuing on? Okay, so, okay. So maybe about half and half. Okay. Well, that makes sense. I just know that this is the last class that you need for that particular business degree. You might still be taking other classes. Okay. All right, well, very exciting. Let's see, we've already done a lot of these things, so I figure I'll just keep on going.
How's your schooling going?
For you is very similar material to what we're doing in here. It's almost identical. So it's kind of wild that I'll be teaching it and taking it simultaneously. They'll focus like on proofs, I guess, like proving that it all works, but it's very similar content, and I'm excited that I get to be taking and teaching at the same time. Yeah, I have taught this course before. I do know the material. I don't want you to think like, oh geez, he's just studying it right now. No, I know the material, it's just I'm taking it at a higher level. Okay, so everybody, as always, you can email me within the next week for extra credit. So go ahead and email me, tell me what makes math easier for you, what makes math harder for you, and a favorite joke, keeping it short and clean. Okay, so that's one thing. Review the syllabus. Let's just point out some key things here. We meet Tuesday and Thursday from 2 to 4:45. We will use all of that time. I'll never let us go early. You know that. And one thing you need for sure is a graphing calculator. Whoa, boy, do you need a graphing calculator, because we'll be using matrix functions quite a bit. We'll be typing a matrix into the calculator, using the calculator to calculate inverses and determinants, and it's so much easier to solve some problems in this class if you have a graphing calculator. So if you don't already have a graphing calculator, I really recommend a TI-82, but no, all of you should have one. All of you should have a graphing calculator. If you don't, you can go online to Amazon and get a TI-82. It does everything that we need to do in this class. Okay? See me immediately after class if you don't have a graphing calculator, because you really need it the whole time. Okay, this class, I know in 213 we all use the program called MORE or Math.AS. In this class, we'll be using Pearson My Math Lab. Now, on the one hand, you might be saying to yourself, oh no, a totally different computer software system to learn. And that's perfectly fine if you want to feel that way. Because that's a metaphor for life, isn't it? Every time you change a job, oh boom, all new computer softwares. Change a job, oh man, now I have to learn new computer softwares. This is the way of life. And the fact is, the more systems that you become familiar with and master, the overall better you are at approaching the next computer system and mastering that system. So we'll be using Pearson My Math Lab. It is, I believe the cost is $100, or maybe it's $95. It's right around there. So I put in the syllabus your instructions for going on to the Pearson website, mymathlab.com, and signing up. The good news is if you sign up, whenever you sign up, you can get 2 weeks for free before you have to pay. So that means if you're waiting on student aid or something like that, you can go ahead and still sign up today when you go home, have 2 weeks of access, and then at the end of those 2 weeks, you do have to pay, normally by credit card or you use like a debit card, any sort of electronic payment. Okay? Questions so far, Ms. Cheryl?
Is that the one you buy at the bookstore?
Yes, you can buy it at the bookstore, or you can just pay right online.
That's one that you sent us earlier this week on the syllabus, right?
Yeah. Okay. Yeah. So My Math Lab is very similar to MORE or Math.AS because it has videos, it has the textbook, and it has the practice problems. And then the practice problems themselves, if you're doing one and you're not sure how to do it, you can click, show me how to do this problem, walk me through a similar problem, and it will tutor you as you go. Okay, so one thing I want to say right up front, that I've never said it exactly like this to any of you before. I really can't stress enough how important it is that you read the textbook and watch the videos before you come to class. And I want to make sure you know that I'm not just saying that on some abstract level. Every time I take a math class through my Emporia degree that I'm seeking, I never watch the lecture without having watched the textbook first. Because I know that that's just death. Like if I just go and watch the lecture, I feel like I'm confused most of the time and I'm like, why is he saying that? Why is he saying that? Where did he get that from? So instead, before I go to class, I take my textbook out and I skim. So that's the first thing I do is I just kind of, look briefly and be like, okay, so this is what we're talking about, okay, I have a general idea. Then I go back to the beginning of the chapter and I read the whole thing word for word. I take notes, I write down every example problem, read the whole chapter. Then I go watch the lecture. And that's the only way I feel like I can survive. Now, I don't know if you identify with that or if I've convinced you, but I really want to encourage you to try that this semester if you don't already do that. I really think that before you come to class, you should skim through the textbook for the section we're doing that day, and then come to class. And I think you'll see it makes a world of difference. It makes a world of difference to preview the material before you come to class. Simone?
Do you have a course ID for Pearson?
Yeah, it's on your syllabus. If you flip due to the very last page there, just right on the back there, it says course ID Gabrielle 74976, and then you go from there. There you are. Good question, Simone. All right. So review the syllabus. This is how you're going to get your grade in the class. We will do notes during class, and then you will get a practice test before every real test, and then you have your My Math Lab assignments that are all online, and then, of course, you have your tests, and then your final exam. Yeah. I think for all of you, it's similar policies to my previous classes. Yeah, I won't read all that. You can read it yourself. One thing I want to make sure you'll know is that I will not round up your grade. I say I only round up if you've turned in all of your assignments and you've done every extra credit opportunity. So for instance, then I'll round up your grade to an A. I'll only do that if you have, in fact, turned in every single assignment and you did every single extra credit opportunity. All right. Is that how I did it last time?
Yeah.
Okay, so you all know that. All right, tardiness and attendance works the same way, but basically when you sign in, if you sign in late, that counts as a tardy, and you get 2 tardies for free, and then starting with your 3rd tardy, I start taking 5 points off your final exam grade. That might be new for you too. Yeah. So you get 2 tardies for free, and then every additional tardy you have, I take 5 points off your final exam, 5 points off your final exam. Same thing goes with attendance. You get 2 absences for free. And then starting with your 3rd absence, you get 5 points off your final exam, 5 points off your final exam. John, how does that make you feel?
It was 1 point last time, so 5 points is a good job.
Yeah, I suppose so. I found that 1 point wasn't convincing enough. But you'll be fine, Adon. You were here early today. You're going to be here every day, right? Yeah. All Okay, so that's tardiness. On the other hand, if you have perfect attendance and no tardies at all, you get extra credit on your final exam. 5 points for no tardies, 5 points for no absences. Okay, required offices. I think all of you have seen this before, that sometime within the next couple of weeks, you have to come to my office and say hello. And then once we start taking tests, if you score below a 70, you have to bring that test into my office and we'll review the whole thing. And then I'll put the grade into the grade book. What else? Okay, this is new. This is new for all of you, so everyone look up here. Before the second week of school, so sometime this week, you have 2 different types of online communication to do with me. First, just do that extra credit email where you tell me what makes math easier, what makes math harder, and tell me your favorite joke. Second, I want you to go into the My Math Lab system, open up the homework, choose any problem, and then click Question Help, and then ask my instructor, and send me a quick question or just say hello. Because I want you to see where within the My Math Lab system you send me questions. So, my goodness, I wonder if I'm able to log into My Math Lab. Because then I can show you. So you just Google My Math Lab. There it is, My Math Lab Pearson. And then let me see if I know my password. Patience. Now, I'm so sorry, I need to look up my password. Does anyone know my password? Can you just tell me my password real quick?
You can tell us.
Okay, well, let me look. Now, okay. My Math Lab. Oh, well, that's reasonable. Okay, let's try that again. Open, yes. I could have the wrong email. I think that's a very real possibility. What on earth would my email be? Oh boy. Well, I don't know why it's not logging in. I tell you what, I'll wait until. This can't possibly do that. Not possibly. This is my personal fear, is wasting time in front of the classroom. Like, you know how you have a dream and you haven't been to class in weeks and then there's a final exam, and that's like your worst nightmare. This is my worst nightmare. Okay, that is it. Aha! All right. So here we go, folks. So, all right, everybody, come on back. Come on back. Come on back. This is my math lab. I just signed in. You're going to find. We're going to go on in here, and then we're going to find our homework. Now, I'm in my teacher logon, but hopefully it's just going to show us where. Oh, there we go. Chapter 1. This looks like an assignment. There we go. So here's the chapter 1 assignment. I'm going to go over here. I'm going to review it so we can all see what it looks like. Here we go. There we go. So here we have it. This is what the platform looks like. So we're in the homework assignment for chapter 1, and it says find the slope of the line if it is defined. Find the slope of the line if it's defined. Okay, through -1, -11, and -510. So basically, right now, I can just go in here and calculate the slope by myself. So let's see. The slope is going down 21 and up 4. Let me try it. Oh, is it going to let me check my answer? Yay, it says good job. Talking about positive reinforcement. So there we go. Now I'll click next question. So that one's done. Let's try this one. Let's say I have no idea. I type in an answer and it's wrong. I'm like, oh no, sorry, that's not correct. And first of all, it gives you a little tip how to do the problem. It reminds you about the slope formula. You say, okay. Well, let's say you try a few more times and you still can't get it. Right up here is question help. Question help has an abundance of options for you. One says, help me solve this. If you click it, it's going to literally walk you through this exact problem. It's going to show you line by line how to go about doing the work. You'll have to plug some things in to interact with it a little bit, like you have to plug in the numbers from the formula. But it kind of gets you started. And then you keep saying, check answer, well done, and then you keep going. Is the quotient fine? No, because it's divided by 0. This word. Close. Now, the problem is, it just showed you how to do this problem, so you can't get credit for it, right? Because it just showed you how to do it. So then you're going to have to try, oh, it gives you a new problem to try. So, but still that's nice. So click question help me solve it. It'll show you how to solve it, and then you get a new problem to try on your own. Or you could just click view an example. And view an example will show you a problem just like it, and it will walk you through the steps, and it won't make you do anything at all. It'll just walk you through the steps. So those are 2 options available to you when you click on question help me solve it, view an example, and then they have a video. The video will walk you through a problem just like it. There we go. I mean, it's literally showing you a problem just like it. Okay, I'm not going to watch the whole video. It also might have an animation, which, if it does, okay, that one goes a pop-up, so blocked it. You can click on the textbook, and no, I did not pop up, so blocked it. But more importantly, here it is, Ask My Instructor. This was the whole thing I wanted to show you, is how to find Ask My Instructor. When you click Ask My Instructor, this feature is not available during preview. It'll open up an email and send that email to me with the problem that you're working on. Okay, so that's what I'd like you to do this week, is just log into Pearson My Math Lab, go right into your first homework assignment, and then shoot me an email, just so I see, you know how to use that feature. Okay? All right, let's go back. So that's your required online communication for this week. So send me a regular email to my long email address, and then send me an email from within Pearson My Math. Okay, so this quiz, you all have it in front of you. Just fill that out and bring it back by Thursday. Review the calendar. Folks, this is the most startling part about this class. How long is that calendar? 8 weeks. Yeah, 8 weeks. This is a very, very short class. It is accelerated. This is fast. So instead of a normal 16-week course, it's only an 8-week course, and the class is almost twice as long. So our class periods are 2 hours and 45 minutes, which honestly is not twice as long as 1 hour and 50 minutes. It's only really an hour more. But the whole week got condensed down into 8 weeks, and that way all the rest of you can take GBS 220 when this class ends in March, and then you start taking the next class. So it's only an 8-week class, folks. I would say, how many other classes are you taking? You're taking other classes right now, right? Right. You might want to bump this one to the top of your list because it's only 8 weeks long. It's going to take more time and effort than a normal 16-week course. Just imagine you have twice as much homework in 1 week so that you can get the whole thing done in 8 weeks instead of 16. So it's really important that you not fall behind, you stay on top of this homework, especially if you're going to take GBS 220 and graduate. So just speaking honestly about the requirements of the course. Now, take a look. The course is very simply formatted. You have one test. So there's test number 1 over chapters 1, 2, and 17. And then you have the next test, chapter 2 test over chapters 3, 4, and 5. Then you have the next test, test number 3, over chapters 7, 8, 9. So I realize that might look a little funny. We're doing chapters 1, 2, 17, and then chapters 3, 4, 5, and then chapters 7, 8, 9. So your test is always going to be over 3 chapters at a time. And then we have a review day for the final exam, and then you take your final exam. So that's what we're doing in class. If you look over here in the right-hand margin, these due dates and the due dates for the assignments are due on these dates, whereas everything that we do on paper is due on the day of the test. So your note packets are due on the day of the test, your practice test is due on the day of the test. Anything we do on paper is due on the day of the test, whereas the online assignments are due on these dates. I know I'm going fast. Does anyone have any questions about all this? Maybe I'm not going fast. You're like, this is great, get this done with. David, like, yeah, this should be okay. Let's get to the mathy part. All right, then that's our calendar. Here's what we're doing. So chapters 1, 2, and 17 focus on solving systems of equations. You know how like you graph two lines at once and then find the point of intersection? We're looking there. Chapters 3, 4, and 5 focuses on matrix applications. So using matrices to solve systems of equations. And then 7, 8, 9 is just kind of a fun section there where we do counting, probability, and statistics. So that's your course at a glance. That's one test, that's another test, that's another test. Okay. And then, if you need help at any point, feel free to see me before class. I have office hours right before this class. I do not have office hours right after this class. I have office hours right before this class. So see me before the class. You can also go to the Learning Center in the IB building. They have free tutoring. You can just email me anytime. You can watch class again because I'm recording all the classes. And definitely read the textbook, watch the videos, and use all those resources available to you on Pearson My Math Lab. Okay. These are your course goals. And I'm going to be a little philosophical now. Your first goal is the mathematical content, of course. Like you're in a math class, so you're learning math skills. We're not going to read poetry or learn science. We're learning math. That's obvious, but learning math is just a metaphor for the overall challenge of learning anything difficult. So as we work our way through this course, just keep in mind, you know, you may or may not use these skills again in your life. Probably you will because it's for your degree. But the main thing is to observe yourself as you come up against a challenge and how do you face that challenge and how do you rise above it. So that's one thing. 2, computer skills and the attitude of mastery. You'll need to learn so many different computer systems in your work, so go into it knowing you can master it. So first of all, has anyone in here used Pearson My Math Lab before? Oh, okay, 3, 4, oh, okay, 5 or 6 of you. Okay, well, great. For those of you who've already used it, you're like, no problem, I've already used it. But for those of you who haven't used it, I predict that maybe the next week, you'll have some feelings of frustration, right? Oh, no, it's a new computer system, I have to learn it. Oh, this is confusing. But, you know, push through that, and then just keep in mind, you can always figure out a computer system. Computer systems are made to be figured out. It just takes time and practice. And then finally, introspection and self-discovery about struggle. So know thyself. What does it feel like to struggle? What is it like to feel frustration and overwhelm, want to quit? Then you catch yourself cutting corners and procrastinating. And then what will help you make a breakthrough? So especially in this class, you need to stay on top of your work and keep up with pace. Okay. This is my invisible syllabus, meaning other than all the stuff that's actually on your syllabus, these are the 2 big things I hope to take away from the course. One is that you'll be able to show all of your work for all of your problems, and I think you all already know the answer to this question. Who are you showing your work for? Who are you showing your work for? Your
Audience.
audience, right? You always have an audience. Your audience is me grading your work. Your audience is your own brain so that you remember how to solve the problem later on. And your audience is your employees, because all of you are going to become managers and leaders in your field of industry, and you're going to have employees working for you, and you sure better be able to communicate how to do a skill so that your employees can learn from you. And that's what doing math is. It's just communicating a skill. So yeah, answers unsupported by work do not earn points. Okay, and then number 2 on the invisible syllabus is the beginning of every problem is to simply understand what the problem is asking, so finding the question mark and knowing what you're looking for, but then drawing a good picture. And all of you know from 213 that we tried to draw a picture with every problem. Right? We were constantly drawing graphs, constantly drawing the XY axis, constantly drawing graphs. We'll do the same thing here. The invisible syllabus is I admire you. All of you. Look at you here once again taking a math class when you could be enjoying some afternoon delight, having an early dinner, who knows what, but no, you're here taking a math class. That's a lot of courage and hard work, and I'll just be here to encourage you throughout the whole semester. And finally, the invisiblist syllabus is my message to you as I want you walking away from this class thinking, I can learn this, I can master this, anything with fluency. I can teach this to someone else, I can use these skills, and I can go out and learn anything I need to learn in order to achieve any goal that I have in mind. Right? Okay, again, I realize I'm being a little philosophical here and just, like, you know, try to motivate you all because it's an exciting course. Okay, so your homework. I posted this on Canvas. Let me see if I can log on to Canvas. These are all the things that I need you to do this week. So let's go on over to Gateway Canvas. And I'm going to log in. And there we are, course 217. So for this class. And on the welcome screen, I give you the syllabus as well as the instructions to log on to my math lab. And if you click on announcements, it has takeaways from day one, and that has a list of all the assignments you are to do this week. So specifically, fill out your student info sheet, your syllabus quiz, and bring them on Thursday. And then go onto Canvas and just browse everything, and go onto my math lab, familiarize yourself with it, and then do the required online communication, which is sending me an email with a joke, and then going into my math lab and clicking on message my instructor. Okay, well that was exciting, we're already done. You all go home. No, but we're done with all that information. So does anyone have any question about the, just the syllabus, or filling things out, or anything at all like that? Simon, what's your question? Okay, Danny, close away. Luis? Okay. Saeed? All right, so everyone's ready to go? Okay. Well, there we have it, folks. Today was an overview, that's what we just did, and we're going to cover chapter 1. Now, look at the calendar. We basically do 1 chapter a day. That's very fast. To do 1 chapter per day is incredibly a fast pace. So that's the goal. Fortunately, chapter 1 is pretty short. It's just 2 sections. But look at chapter 2. There's 5 sections in chapter 2. That's a lot of material to get through. And then chapter 17, 4 sections there. That's a lot of material to get through. That's why, like I said, it's very important that before you come to class, you at least flip through the book and look at all the topics that we're going to be covering. Even if you don't master the material, just flip through it. So we have 3 days to do material. We have a catch-up day, then a review day, and then you'll take your first step. Okay, doke. Well, I have a joke for you. But I realize now that you've all taken my class before. And so you probably maybe remember this joke. So I think for you all, I'm going to have to start coming up with new jokes. So I'll tell you the joke that I already have, but then I'll tell you a new one I just heard because it's very cute. So first of all, what did the pirate say when he turned 80?
Nine.
No.
Got it.
Aye, matey. Yeah, there you go, yeah. He does say I'm 80. Okay, so I just heard this one, it's very cute. One nut is chasing another nut. And what did the nut chasing the other nut say? I'm a cashew.
I
Cashew.
the best dad jokes.
Yeah, it is a dad joke. All right, well, what's that, David?
At least it was new.
At least it was new. Exactly right. Yeah, that's a great attitude to have. Okay. So let's see here. User notes for chapter 1. Everyone go ahead and take a look at the chapter 1 notes. Now, here's the thing. The whole first big chunk of that packet is review. It's really, really, really big review of material that you've done your whole life over and over and over again. And so what I did was, at least for the first like 10 pages, I went ahead and I filled out a good amount of it, and then I scanned it, and I'm going to post it online. So you'll have like an answer key. And that way you can kind of go in and see it. So my question for you is, how much of this little review should we do? Right, it's a review of linear equations. I was thinking maybe, we could do 1 or 2 problems per page just to kind of get our brains in gear of solving problems. But otherwise, what I really want to do is get all the way to this page where it says Mathematician Chapter 1 notes. So can I get some feedback from you folks? How much of a review of linear equations would you like to do?
Is there like a problem or two like each one just to kind of get warmed up?
Okay, does that sound acceptable to everybody? That we might just do 1 or 2 problems per page just to remind all of our brains every day? Okay, I think that's probably a good idea.
If you're posting the key, then we can always just go in and just check it.
Yeah, you can always go back and look. Okay, so yeah, this will be a very speedy review of linear concepts. I posted a partial solution key online. So, first question, find the slope of each line. So what's the definition of slope? You can put it on your paper. The definition of slope is? Very good, rise over run. You can say rise over run, or as you know, I always say the up down over the right left. So you've got slope, rise over run, or the up down over the right left. And when we look at slope, the up is positive, down is negative, right is positive, left is negative. But yeah, you could also call it rise over run. So finding the slope of each line, we'll do the first four. We typically go from left to right. So to go from this point to this point, now first of all, you always say the up-down part first, and then the right-left part. So I'm going to call on all of you. So let's start with, here's Simone. How do I get from this point to this part? Say the up-down first.
Go up one,
Very good, up one.
right, yeah, wait. Okay. 1, 2, 3, 4, 5.
Very good, up one, right five, so the slope is 1/5. That's it. Up, down, over the right, left. How about the next one, Sarai? How do I go from the point on the left to the point on the right?
Down.
Down?
One.
Yeah, down one, and then? Yeah, right 8. So that slope is simply negative 1/8. Okay, very good. How about this one? Now maybe, of course you can always count it out, but maybe you just know this slope off the top of your head. Well, wait, what's this slope right off the top of your head? This slope is 0. So you can just say 0. You don't have to go through the process of saying up 0, right 3. You can just say it's 0 because that's a 0 sloping line. What about this slope right here, Bata? What's this slope? John, that is correct. Bata, what's this slope? Well, you should stop doing that. Follow along. So what's this slope right here? This is a 0 slope because it's horizontal, and maybe you all want to remind yourself it's horizontal. Whereas this line is vertical, so what's that slope? 0. It's not 0. This one over here is 0 slope. Going this way, it's undefined. Very good. Okay, so this slope is simply undefined. All right. Well, there we go. Those are your basic types of slope and how to use the up, down, or the right, left to calculate your slope. So let's keep going. Slope or sketch a graph. Sketch a graph of each line. So we'll just do a couple of these. How about the very first one? Now, first of all, let's just remind ourselves. What's the equation of a line? How about here, Michelle? What's the equation of a line? Y equals, yeah, very good, mx plus b. And what does the m represent? Yeah, the slope, and what does the b represent? Yeah, the y-intercept. All right, very good. So for instance, this first one, folks, you always plot the y-intercept first. The y-intercept is -3. And then my slope is 4/5. Again, that's the up, down, over the right, left. So my slope is +4/5. That means up 4, right 5. So I would go up 4, right 5, put another point, and there's my line. Now, believe it or not, we are actually going to be graphing quite a few lines in this course, because we'll be solving systems of equations. So walking through the next one. Luis, what's my y-intercept? And what's my slope? Now this one's tricky, folks, because it just says -8/3. Where do I put the negative sign? Yeah, either or. Where do you want to put it?
So we're gonna go.
What do you want to put on the top or the bottom?
The -3.
Okay, so Luis is choosing to put the negative sign on the 3, which is just fine. You can put it on top or bottom. So how do you read it then?
So up 8.
Up 8. And then?
Up 3.
Left 3. Okay, very good. So you go up 8, left 3, put a dot, and then a dot. So that's a good review of what to do with negative signs. The negative sign can either go on the top or the bottom. It's up to you how you want to interpret it. Alrighty here. And how about Sadia? How do I interpret this slope right here? Because the slope needs to be a fraction. Yeah, put it over 1. Okay, Sadia, tell me, where's the y-intercept? 2, and what's the slope? How do you read that as up, down, right, left? They're both positive. Yeah, up 2. One what? Right, yeah. Up to right one, up to right one. And what's the opposite of up to right one, up to right one, up to right one? David. Yeah, down to left one, down to left one, down to left one. Okay, very good. All right, and then folks, what do you do if there's no number at all in front of the x? Like, let's go down and look at number 23. Diego, what's the slope on this one for number 23?
1 over 1.
Yeah, 1 over 1. If there's no number, it's a 1, and you put the 1 over 1. So Diego, where's the y-intercept?
-3.
And then how do you read that slope?
1 right 1.
Yeah, up 1, right 1, up 1, right 1, up 1, right 1, or down 1, left 1. Yep. Alrighty, turning the page. Finding the slope between given coordinates. We'll definitely do this quite a few times in the context of word problems. So probably the best recommendation would be to first write down the slope formula. What is the slope formula? This was the definition of slope. What's the slope formula?
Positive y minus y1
y2 minus y1.
over x2 minus x1.
Yeah, x2 minus x1. And to be fair, you could also write it as y1 minus y2. So long as you're consistent of it's 2 minus 1, 2 minus 1, or 1 minus 2, 1 minus 2. Now, so long as you're writing down all those definitions, it's important that you then label the coordinates as well. So like, for instance, this one would be x1, y1, and then this one would be x2, y2. And then recall the idea of writing something empty. I'll write down the slope formula as something minus something over something minus something. And now that I wrote that slope formula empty, I can just go in and plug in all my numbers. So what numbers do I plug in? I think I've called on everybody now. Postway? What numbers do I plug in?
All right.
5 minus
1,
1, and then
11,
11 minus
-7.
-7. Very good. So that gives us 4 over double negatives, chop, chop, that's 18. And then we have to simplify that to be what, 2/9? Now, would you take 2/9 and write it as 0.22222 repeating? Yeah, maybe, right? I mean, technically, since it's a slope, we want to leave it as a fraction because slopes are fractions. But on the other hand, if the slope represented something, like the interest that you're earning per day or the money you're earning per day, then a decimal representation might be a good idea if you want someone to know that you're earning 22 cents a day. So it really just depends on the context. Okay, well that's the slope formula. I know, again, I'm going through all this part fast. At some point, we're going to slow down and do these word problems. But anyone have any questions on this?
Okay. Would you want us to just leave it in fraction form or break it down to decimal form?
I think it depends on the context. If they're asking for a slope, you'd leave it as a fraction. But if the slope represents something like money, you'd put it that way. Okay. This next page is, and this is important. Well, I mean, come on, it's all important. This next page is saying, I'm giving you an equation that looks like this. All right, everybody, let's go straight on down to number 40. I'm giving you an equation that looks like this. Now, first of all, why would we want to be dealing with an equation that looks like this instead of, say, the equation that says y equals 2 over 1x plus 2? All right, so this right here is slope-intercept form, y equals mx plus b, and that's what we're used to dealing with. Whereas this is not slope-intercept form. What is this called? And maybe everybody should make a note of it at the top. This is called standard form. Standard form, which is ax plus by equals c. And here's our first example, 2x minus 1y equals -2. Standard form is just another way of representing a linear equation. Standard form is not convenient for any of the reasons slope-intercept form was convenient, because just looking at this, do you know what the slope is? No. Do you know what the y-intercept is? No. So right off the bat, you might say, gosh, why would we ever deal with standard form? It seems pretty inconvenient. But the reason you would deal with standard form is, let's just say, here we go, that I were to give you two standard form equations, like 2x minus y equals -2, and 7x plus y equals -2. Well, now you have a system. And in a system of linear equations, you want to graph both of them. So let's just pretend that this is what the graph looked like. And you want to find the point of intersection. So sometimes we look at standard form equations instead of slope-intercept form because we're leaning towards solving a system of equations, which means you're graphing two lines simultaneously to find the point of intersection. Now, who remembers a quick and easy way to solve this system? To find the point of intersection. And you solve two equations simultaneously. Well, you could, I mean, they're both equal to -2 by some fluke. Yeah, theoretically you could, but that's not the way we want to do it. There were two, not assimilation, but you're very close. What? You could either use substitution or elimination. Exactly right. So remember substitution and elimination. We'll spend all next class period in chapter 2 doing substitution and elimination. I'll just remind you really quickly right here, what can we eliminate? The plus y and the minus y. So if we add these two equations together, the y's cancel out, and you get 9x equals -4, and then you can finish solving for x, and you get x equals -4/9, which happens to be -0.4444. So that tells us that the x value of the coordinate of the point of intersection is -0.4. So all this was just to kind of suggest why people would bother with standard form equations. We actually are going to use standard form equations a lot in this class, not just because of the systems approach of solving a system, but also because when you just take the coefficients, 2x minus 1y, 7x plus 1, and you turn it into a matrix that looks like this. 2, -1, -2, and 7, 1, and -2. Does that look familiar? Yeah. Okay, like we're spending a lot of time on this. Hey, Lorena! Lorena was in this class last semester. A whole year ago, you were in mat217, 218. Remember all those matrix methods?
This is fun.
I know, seriously. Okay, yeah, so standard form equations lend themselves to matrix methods. And we're going to spend at least 3 or 4 chapters doing matrix methods. Okay, I'm just kind of pointing things out right now. Okay, we haven't even done a problem on this page. I'm just showing that instead of y equals mx plus b, which is handy for graphing, you also have ax plus by equals c, which is handy for solving systems, and it's handy for doing matrix methods. So back to the original question, what if they gave you a standard form equation and you want to turn it into slope-intercept form? How do you do that? How do you turn this back into y equals mx plus b? Everybody write it down. 2x minus y equals -2. How do I convert this into y equals mx plus b? Solve for y. Solve for y, very good. So we're just going to get y by itself. First, I'm going to move the 2x over to the right, so that's a positive 2x. I'll subtract the 2x from both sides, and that gives me -1y equals -2x minus 2. We're almost there. You'll notice I turned the -y into -1y, because if you don't have a number in front of a variable, you might as well put the 1 there. So now how do I finish solving for y? Yeah, just divide off the -1, divide everything by -1, and we end up with y equals 2/1 x plus 2. And now that's in slope-intercept form. So I'd like all of you to go ahead and try that for number 38. Take the equation, take the standard form equation in number 38 and solve for y. right, who'd like to walk us through it? The volunteer in the house. Sadia, thanks for volunteering. What do we do? 6x minus 5y equals 20. What do I do first? Yeah, minus the 6x, move it over to the other side. That gives us negative 5y equals negative 6x plus 20. And then divide everything by negative 5. And did everyone get y equals positive 6/5 x minus 4? Is that it? Okay. Now, what we're saying is we have two very different ways to think about linear equations. You can either use slope-intercept form. Slope-intercept form is good for graphing. Or you can use standard form. And standard form is good for solving systems and using matrix methods. And if they give you a standard form, you can easily turn it into y equals mx plus b by simply solving for y. And that's what we just did. But what if you want to go the other way around? What if somebody hands you y equals 6/5 x minus 4, and they said, convert that to standard form?
6 over 6, 5x equals y minus 4.
What do you say? You're saying you want to move the x term over?
Yeah, in terms of.
And that's absolutely true. I mean, think of our goal. We want x and y on the left, and we want a number on the right. So that's true. We do want to move the x term over. What else will we want to do? Because, and maybe I didn't say this right up front, a, b, and c have to be whole numbers, not fractions. How do we get rid of the fraction?
By over 6 over 5. Like,
Well,
multiply
you-
over by 6 over 5.
You can multiply by the reciprocals, 5, 6, and that'll get rid of the whole number. Or you can just multiply by the denominator. And that's all that's necessary. So folks, the first thing we'll do is just multiply through by the denominator. So everybody do it. Take the entire equation and multiply through by the denominator 5. So you distribute the 5 to each of the 3 terms. And so first you have 5y, and then the 5 times 6/5 cancels the 5 on the bottom, so you have 6x. And then 5 times the negative 4 is negative 20. So yeah, you cancel a fraction by multiplying through by the denominator. Then we just move the 6 term, or the 6x term over. So we write minus 6x minus 6x. And now we have negative 6x plus 5y equals negative 20. Okay, there's one other thing. Typically, when we talk about standard form, A, B, C are all whole numbers, and A is typically positive. How do we make this positive? We can just multiply through the whole thing by negative 1. And of course, multiplying through the whole thing by negative 1 has the same effect as what? Just changing all the signs. Yep. So that's how you take a standard form equation and turn it into slope-intercept form. You solve for y. And that's how you take a slope-intercept form and turn it into a standard form. You get rid of the denominators, move the x and y to the left, and make sure the x term is positive. What questions would you like to ask about that? Yes, Luis.
You said typically.
Typically, the first term is positive. That is, if you look in textbooks, they'll typically tell you that the A term should be positive, just as kind of like standardizing it so that everybody's on the same page. But sometimes in some applications, like I bet some of the problems that we do in this class, I bet sometimes the first term isn't positive. It's just the standard. The standard form. It's just how it's usually done. I can't say anything better than that. I mean, you know how you're never supposed to begin a sentence with and? People do it, but it's advised against. And you're not supposed to end a sentence with a preposition, so people do it. It's just advised against. Okay, so maybe it's more like style. Okay, great question, Luis. Anyone else have a question? Okay. What? No? Okay. All right, folks. So next, I think we could probably, we can skip that page entirely. Just cross a big old line through it. Find an equation line graph, you can cross that out. Using point slope form. This will be helpful. Let's review real quickly point slope form. We have now seen slope intercept form, y equals mx plus b. We've seen standard form, ax plus by equals c. And who remembers point slope form? Yeah, y minus y naught equals m times
X minus X naught.
yeah, very good. Okay, so there we go. Those are the 3 linear equations that we use in mathematics. So slope-intercept form is good for graphing, standard form is good for systems and matrices, and point-slope form is good for finding the equation of a line. So like this whole page, they're asking you to find the equation of a line that goes through that coordinate with that slope. This actually comes up a lot because they'll say things like, you know, you're making textbooks and you sold 1,000 textbooks for $42,000 and you're selling textbooks for $20 each. How much will it cost you to make 5,000 textbooks? And so they asked some question that you needed the equation for. So let's go ahead and try using point-slope form. Oh, there it is right at the top. Did you see that?
I didn't.
All right, way to go. Okay, so we want to find an equation that goes through the coordinate 4, 4 and has a slope of 1/2. Now, first of all, folks, keep in mind, drawing good pictures, you can always just draw a picture of that. Here's the coordinate 4, 4, and here's the slope up 1, right 2, down 1, left 2, down 1, left 2, down 1, left 2, and whammo, I already have my line. I already have my y-intercept is 2, so I can go ahead and just write down the equation y equals mx plus b is y equals 1/2 x because they told me the slope, plus 2 because I just found the y-intercept by making a graph. Okay, so just so we all know, any problem that you can solve with an equation, you can solve by drawing a picture. So now, how do we do that same thing using point-slope form? First, everybody write it down once. Y minus y naught equals m times x minus x naught. And now, just to remind you all of this technique called write it empty. So you're going to write y minus blank equals blank times x minus blank. And that's point-slope form empty. Because now what we're going to plug in is the x naught, y naught, and the m. They gave us the coordinate, that's your x naught, y naught. They gave us the slope, that's your m. So this is a good best practice for setting up a problem. Is you write the formula for point-slope form, you write it empty, you label the information they gave you, and then you just plug it all in. So y naught is 4, x naught is 4, and the slope is 1/2. Now what do we do? Because ultimately what they want is y equals mx plus b, or standard form, either way. But they don't want us to just leave it like this. They want us to simplify. So what are our simplification steps? Yeah, distribute, and then? So we're going to distribute first. So that gives us y minus 4 equals 1/2 x minus 2, because half times x is half x, and half times 4 is 2. And then we add the 4 over to the other side. And then we have y equals 1/2 x plus 2. And sure enough, that matches the equation that I derived visually by just drawing a picture. All right, so that's point-slope form. What's your favorite? I'm just going to take a little poll here. Whose favorite is y equals mx plus b? I would have thought everybody. Okay, 1, 2, 3. Okay. And whose favorite is standard form? Luis, it is? That's awesome. Okay, and whose favorite is point-slope? Boom, I can't believe it. All right, a couple people. All right. Well, folks, I think that's all there is to say right there. That's point-slope. They're all tools that we have. All right. Oh, good. Oh my gosh, I think we're almost done. We are almost done. This is so wonderful. Like done with just this little review stuff. All right. Here it says, write the slope-intercept form of the equation of the line described. Now, folks, I just want to say, these are good problems. I would say that, first of all, the problem is very simple. This is very easy to do. It just takes a couple lines of work. But if you went up to just about any American on any day of the week and you said, hey, find the equation of the line that goes through that coordinate and is parallel to this line, how many people do you think would be able to do it? 0. Yeah, like very close to none. Right? Because it seems hard. It seems hard, like, oh, gee, I don't know how to do that. Well, folks, the fact is you do absolutely know how to do this. This is a great example of a word problem. I mean, it's barely a word problem. It says, find the equation of the line through that coordinate parallel to that. It's a very short word problem. And it's easy to compute, but you have to remind yourself how to conceive of it. So everybody, let's begin by drawing a picture. let's go ahead and draw a picture. Just a little graph. We want a line that goes through the point 1, 2. So let's draw that coordinate. 1, 2. There's our coordinate. And we want a line that goes through that point. So for sure we know it goes through that point. But we want our line to be parallel to y equals 7x plus 2. Well, where's that line? First of all, what do I do to 7?
Put a 1 under it.
Yeah, put a 1 under it. Okay, so let's find that line. That line has a y-intercept of 2, which is there. And then the slope is up 7, right 1. Up 7, right 1. So I'm going to go ahead and do up 7, 1, 2, 3, 4, 5, 6, 7, right 1. And so there's the other point. Or instead of going up 7, right 1, I could go down 7, 1, 2, 3, 4, 5, 6, 7, left 1. And there's the line. So that's the setup. Somebody walked up to you and said, I would like a line that goes through that point right there, and I want it to run parallel to the blue line. So conceptually, do you know what the problem is asking you for? What are they wanting to find? They want a line that goes through this point. Does the blue line go through that point? No. No. So definitely the blue line is not what they're looking for. That's the blue line. They want a line that goes to this point and is parallel to it. So everyone take your own pencil and draw a line through this point that is parallel to the blue line. It has to be parallel. And did you all draw something like this? That's what they want. They want to find the equation of a line that goes through the point 1, 2, and they want it parallel to the blue line. So what do we want? We want the equation of the red line. And so what is the equation of the red line? Do we know the slope of the red line? What's the slope of the red line? 7 over 1, right? I mean, it's parallel, so that is 7 over 1. What's the y-intercept of the red line? Because remember, we're trying to write down the equation of the red line, y equals mx plus b. And the only way we can write down the equation of the red line is if we find out m and if we find out b. M was easy, they told it to us. What's the y-intercept? Yeah, I mean, it's negative 1, 2, 3, 4, or 5. I don't know. My drawing isn't that good. Right? My drawing is not good enough to tell from the drawing. It could be negative 4, it could be negative 5. Maybe if I had drawn a better picture, we'd be able to know for sure. But since we don't have a good enough picture, what do?
Do some math.
We do some math, that's right. We're going to use which one? Are we going to use y equals mx plus b, standard form, or point slope form? Point slope form. So now we go ahead and say, all right, point slope form, y minus y naught equals m times x minus x naught. And then you write it empty, y minus something equals something times x minus something. And then we plug in all the information that we know about the red line. Coordinate that goes through the red line. That's the 1, 2 coordinate. So that's my information for the red line. It goes to the coordinate 1, 2. And I know the slope of the red line as well. That's 7 over 1. But I'm just going to write 7. Why would I just write 7 instead of 7 over 1? That's easier. We don't need to be bogged down with this 7 over 1 business right now. We're just trying to distribute and solve for y. So we distribute. And then we have y minus 2 equals 7x minus 7. Add the 2 over. And we get y equals 7x minus 5. Is that what we thought? Was negative 5 one of the possible y-intercepts that we thought about? Yeah. Okay, so was that a hard problem? I mean, it's not hard, but is it many steps? It's many steps. Now, given everything that we just did, can you do this problem with less work?
Yes.
How could you do this problem with less work? What would I start by writing down? After all, keep in mind, we're going to use point slope form, and we want the coordinate that the red line goes through, and we want the slope that the red line is parallel to. So what's the relevant information over here?
The point.
Yeah, the point, that's our x naught, y naught, and the slope. That's our m. So We don't have to do all that modeling business, drawing a picture of it all. We could just write down y minus y naught equals m times x minus x naught, and then write it empty, y minus something equals something times x minus something. And then we plug in the information that they give us, which is -1, -3, 1. But see, in this problem, we're just diving in, right? We're just diving right in with point slope form under the assumption that you know what this information represents and how to use it. The safest thing to do is to start by drawing a picture. So what do we got? Double negative, y plus 1, distribute the -3, -3x plus 3, move over the 1. Did everyone get y equals -3x plus 2? All right, well, there's that. Now remember, these problems were called find the equation of a line that goes through that point and is parallel to that other line. So what's the other type of question they get asked? Oops. Find the equation of a line that goes through that point and is perpendicular to another line. So what if we want to be perpendicular to another line? So everybody, do you remember the relationship? Well, first of all, what's the relationship between slopes and parallel lines? The slopes are, what, Cheryl? Yeah, they're the same slopes. What do you know about slopes of lines that are perpendicular? Like what if I have this slope, which is up to right 1? What is the perpendicular slope? Well, that's absolutely correct, Josue. When you have two perpendicular slopes, if you multiply them, they equal -1. That is a fact. It doesn't necessarily help us speedily know what this one is, but you are correct. When you multiply perpendicular slopes, the product is -1. How do you change this slope to get this slope? It's just a phrase. It's called the negative reciprocal. Has anyone heard that phrase, negative reciprocal or opposite reciprocal? What you do is you change the sign, so positive becomes negative, and you flip the numbers -1/2. This is called negative reciprocal. Reciprocal. What does reciprocal mean? Yeah, flip the numbers. And negative, another word for negative is opposite reciprocal. They're opposite reciprocals. And what that means is that the signs are opposite. So if one slope is positive, the other slope is negative. And that makes sense. If they're perpendicular, one is pointing up and the other one should be pointing down. Everybody, let's try this. What if I gave you the slope positive 2/3? What is the perpendicular slope to that? And Josue, since you knew about the multiplying to be -1, you get to go first. What's it? -3/2. Did you say -3/2? Yeah. -3/2. Okay, folks, take a look. These two slopes are perpendicular because the signs are opposite and the numbers are flipped. How about this one? -5/7. What is perpendicular to -5/7? Sarai? Yeah, positive 7/5. And now, folks, you'll notice, remember Josue said that if you multiply them, they should equal -1. What happens when you multiply straight across? The 3's cancel, the 2's cancel, positive times a negative is negative. And again here, the 5's cancel, the 7's cancel, a negative times a positive is negative. So it's true, perpendicular slopes do multiply to equal -1. And in order to find a perpendicular slope, you change the sign, flip the numbers. I think everybody should write that down. Change the sign, plus flip the numbers. That's how you find perpendicular slopes.
I have a question.
Oh, I'm so glad, Simone. Questions are the beginning to wisdom.
Yeah, it's not about this. I just want to know, like,
My favorite fast food restaurant has got to be Subway. They have low-calorie options that are very tasty and they fill you up.
oh no, it's not.
Thanks for the question. Go ahead, Simone.
When do we have a break?
We don't get breaks in this class.
No,
Yeah,
we
2 hour and 45-minute class, Simone. You don't get a break. No, wait a minute. Let's see. It's 3 o'clock. I know I put it in my phone. Let's just see my phone. I put the break at 3:30. I put the break at 3:30.
Okay.
However, this was the last problem we were going to do, and then I was going to let us take the break now. So I don't know, folks. I mean, it was totally arbitrary that I chose 3:30. In general, what do you think is a good time for a break? Between 2 and 4:45, 330 was the middle, but we could do it at 3.
Like 3:30, 3:15, 3:30.
Or even 3:15. I mean, 3:15 is what we're going to end up doing today. So let me change my phone here. I'm going to do 3:15.
It's up to you. I just have to go to the
Simone, is that acceptable to you?
It is fine. Thank
Okay. All right, let's do 3:15 then. Okay, so let's finish this last problem, folks. We want to find the equation of a line that goes through that point and is perpendicular to this line. So first of all, what's the slope of this line? That's the slope of this line. But I don't want to be parallel to that line. I want to be perpendicular to that line. So what slope am I going to use, Simone?
you.
Yeah, positive 1/5. I'm going to use positive 1/5 as my slope, and I'm going to use this coordinate that they want the line to go through. So there we have it. That's our x naught, y naught, and this is the slope we'll use, the perpendicular slope, not the parallel slope. So we say y minus y naught equals m times x minus x naught. And then y minus something equals something times x minus something. And then we plug in that information that they gave us. So -5, -5, and the slope is 1/5. And then as always, we distribute. So that's chop, 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 y plus 5 equals 1/5 x. That's another chop, chop. That's positive. Plus 1. And then we subtract 5. We get y equals 1/5 x minus 4. So there we have it. That's the equation of a line that is perpendicular to that line, and it goes through that point. Questions about what we just did? Well, let me say something. What we just did by doing all of that is we just reviewed all the linear theory that you ever learned in your life. Did it feel as exciting as that sounded? You just reviewed all the linear theory you've ever learned in your life. And it's kind of true. So those are all the things that you've ever done using linear equations. And now all of that simply forms the baseline information that we're going to use to now move forward and solve more complex problems that are real-life word problems applicable to business. So, yep. So now we're about to begin where it says Mathematician, Chapter 1 Notes. So everyone flip to that page where it says Mathematician, Chapter 1 Notes. And what I'd like you to do is make a note up there, circle Chapter 1 Notes, and write, this is my math lab homework. Let me explain that, okay? So these problems are just like the problems that you're going to see on my math lab. So everything we just did was just a review. That was just a friendly review because I care about you and I wanted your brains to remember all that stuff. But now this, going forward here, the next few pages, I printed these off from the Pearson My Math Lab site based on the problems that are assigned to you for homework. So starting right here, this is what you're going to get credit for. This is what I'll collect on the day of the test. So you need to do all the work I show, solve every single problem, and then on the day of the test, you're going to turn this in as your notes packet. And furthermore, you can use these as your notes to now go home and do your online homework on My Math Lab. Okay? And that's typically what I'm going to be giving you every week, or every class period that is it'll say Chapter 1 notes, Chapter 2 notes, Chapter 17 notes, and the notes are aligned with the online My Math Lab homework. Does that make sense? So Simone, this is a very timely time to take a break. It is 3:11. Let's come back at 3:21. And we will proceed with our excitement. Study it. How was all that? Yeah, what we just did, did you remember it all? Did it make sense?
Yeah.
Okay. Oh, sir?
Can you give me a seat?
What?
Can you give me a chair?
I'm stretching my back.
Oh.
I find that a squat is the best stretch for my back. But no one's letting me sit down.
I have a bunch of extra chairs.
Yeah, there are.
I hear you got it, but far from home. You watched it.
No, it takes place. It's a long way. That's a struggle. Look at that year. This is the one. Wow. Cheryl? Here, actually, I'm going to collect it on Thursday.
Yeah, I'm gonna say.
No, you won't forget. I'll ask for it. Nah. All right, folks, I think we're ready. Do we have everyone back? Don't think so.
I have a question before I start.
Yeah, what's that? Oh. Now you're going to pay attention to, right?
No.
What? Okay, what?
Yeah, because I was so this is like a sample.
Well, by that, it just means those sections. Yeah. It's in my map.
So this one.
Yeah, this just to tell you what the set was. There's nothing. You have to go to my map. Yeah. Oh, you just have to go to the website. If you just Google my map,
Zero and we're gonna go yo. Zero.
All right, let's get started. All right, everybody, we're on this page together. We're all on the same page, huh? I think that's where that phrase comes from. All right, now, folks, moving forward, you can expect your problems to look like that, right? It's just word problems, because that's what business is. Business is just a bunch of word problems, and then you got to suss it out and figure it out. So it says here, after 2 years on the job, an engineer's salary is $50,000. her salary was $62,500. Okay, so what can you say about her salary?
Increased.
It's going up over time, that's great. Let Y represent her salary after X years on the job. Now, right now I'm just reading it, but as soon as we can, we should start writing things down. So she just said that Y represents salary and X years on the job. Let's start a graph. So the Y-axis, the X-axis, Y is her salary, that's dollars. X is years on the job, that's years. And before we keep going, we can now probably backtrack and include the information they already told us. So years, 1, 2, 3, 4, 5, 6, 7, 8. 2 years on the job, 7 years on the job. After 2 years on the job, her salary was $50,000. There's one coordinate. And then it says after 7 years on the job, her salary was $62,500. So 7 years on the job. Yeah. Okay. Now, assuming that the change in her salary over time can be approximated by a straight line, and that is a big assumption, isn't it? I mean, who knows if that's how our salaries really work? Do our salaries really go up linearly over time? I don't know. I mean, I suppose on the one hand, that'd be nice, because sometimes people get into a job and their salary doesn't go up at all. They just stay at the same salary forever. So I would totally take a linearly increase in salary. That sounds fine by me. Obviously, I wish that it'd be exponential, but I'll take linear, right? So assuming that the change is a straight line, give the equation for this line in the form y equals mx plus b. Okay, so that's it. What do they want? They want an equation for that line. So what would be the best way to do this? Remember, we have three options. We have y equals mx plus b, we have standard form, and we have point slope form. Standard form is right out, right? Standard form, we have a graph here, so there's really only two options, slope-intercept form or point slope form. Which would be easiest, do you think? Yeah, probably point slope. Point slope is probably the most standard way to go about this, just to get the job done. So to do point slope form, what do you need? You need a slope, and you need a coordinate. What did they give us? Yeah, so far they only gave us a coordinate. They gave us 2 and then 50,000, and they gave us 7 and 62,500. They did not yet give us a slope, but they gave us 2 coordinates. Okay, well, we need slope and only 1 coordinate. So they gave us slightly different information than what we really needed to solve the problem. So what do we need to find? What do you think we need to find first? Probably the slope. Now the slope, the good news is you can do that visually from the graph. You don't even have to do slope formula. You can just say, well, we go up, down, over, right, left. So how far up did we go? We went up from 50,000 to 62,500, which you can probably do in your head. So far my slope is up. How much money? How much of a raise did she get? 2,500. Oh, 12,500. Yeah, there we go. So 12,500, and that's the up, down, right, left. How far to the right? From 2 to 7. 5 years. 5. So now we can go ahead and divide that. How many times is 5 going to 12,500? I think 2,500. That's 2,500 over 1. Now this is a great example of how should we report a slope. In this case, our slope is rise over run. That means dollars over time. So that means $2,500 per year. And again, I would take that. I would take a $2,500 raise per year. That sounds great. I think we all would take that. Would it make sense to just convert this into 2,500? Well, you just lost a little information, right? Because the point is, it's not just $2,500. It's $2,500 per year. So the per year is actually quite important, so you want to leave it as a fraction. Okay, so now what do we need to know? We know M, now we need to know P. So we're going to take all this information now and put it into point slope form. So again, point slope form, y minus y naught equals m times x minus x naught. Now you write it empty. Y minus something equals something times x minus something. And in this case, we know our slope now. Now, even though I just sat there and told you to keep it as a fraction, we're about to do a computation, so there's no need to write it as a fraction. You can just write 2,500. And then which coordinate do you want to use? 250,000 or 762,500? Yeah, might as well use this one. It's easier. Why would anyone want to use that bigger number when you could just use the smaller numbers? So now that's going to be y minus 50,000 and x minus 2. And then as before, we distribute and solve. So y minus 50,000, oops, 50,000, not 5,000, 50,000 equals 2,500x minus 5,000, which adding the 50,000 over, we get y equals 2,500x plus 40. How did that feel? Did it feel okay? And that's the basic procedure, folks. Yeah, you read the problem, you capture the problem in a good picture, you make a game plan, in which case we knew we needed y equals mx plus b, and we knew we were going to need point slope form to get it. To do point slope form, you know you need a slope and a point. We already had 2 points, but we needed a slope, so we found the slope visually, and then we just plugged it all in and we got it. Now, what does this tell you about her hiring wage? How much money did she make when she was hired? When she was hired, how many years had she worked? 0 years. And if you plug 0 into this equation, if you plug 0 in right there, what's her salary? 45,000. So that was her starting wage, right? So starting wage was 45,000. Some people might shake a stick in that, say, no, I don't want that job. It only pays 45,000. But then you say, well, you get a $2,500 raise every year. You might want to go ahead and take the job. Okay, well, that's it. That's the whole job. I mean, that's the whole problem. Did we do it? We did it. Okay, let's take a look at number 2. Now that you've seen how to do a whole problem, we might not solve all of number 2. We might just set it up. So suppose that the population of a certain town, what's the name of the town? Anybody know the town?
Simonville.
What is it?
Simonville.
Steamoville.
Simonville.
Oh, Simonville. That's right. Obviously, I should have known. Simonville. Okay. Simonville. In thousands was 105 in 1990 and 141 in 2002. Now, did Simonville only have 105 people in it? How many people were in Simonville? 105,000. So there's actually 105,000 people, and then there were 141,000 people in it. So that happens a lot where they just give you a number, but they tell you the units. So it's not just 105 people, it's 105,000 people. And that was in the year 1990 and in the year 2002. So can you all already imagine the graph we're about to draw? We've got time, we've got population, and they've already given us 2 coordinates, haven't they? Don't put any more details yet because we're not ready to put any more details, but at the very least you know how to start the picture. Assume that the population growth can be approximated by a straight line. Okay, good. Another straight line problem. And then find the equation of the line which will estimate the population of the town in thousands in any given year since 1990. So what does that since 1990 tell us? When we label our graph, do we want to start labeling 1990, 1991, 1992, and so on? Why, I mean, we could, but why don't we want to do that? What's the big gap in between? What, a year? No. Oh, well, yeah, that's true. It's going from 1990 all the way to 2002, so that is 12. So it's not like we want to label 12 tick marks. But I mean using the numbers 1990, 1991. Do you really want to input into an equation 1,991? Probably not. What numbers do we want to use? Where do we always start time at? 0. That would be the year 1990. That's 1991. That's 1992. That's 1993. And then we get all the way over here. What year is 2002? How many years since 1990 is the year 2002? 12. So that's how we want to do it. You want to keep your axes simple by using simple numbers. So now we can go ahead and say, let's go back to the beginning. And it was 105,000 in 1990. Now remember, this is 1990, 0, and this is 2002, 12. So in 1990, which was times 0, the population was 105, which is actually 105,000. And then, so that's our first coordinate. And then in 2002, the population was 141, but that's really 141,000. There. And so here's our line. Now notice that most of these numbers don't represent exactly what they seem to represent. That's not 105 people, it's 105,000 people. And that's not year 0, like the birth of Christ. That's the year 1990, right? I mean, that is year 0, right? That was theoretically BC, AD, so that would be the birth of Christ. Okay, so yeah, you have to be careful about what all our numbers represent. So now what do? We want to find the equation of the line, right? So that's what we do. We can go ahead and just say this is the coordinate 0, 105, and then this is the coordinate 12, 141. And then you go about doing the same procedure we just did. So we will not do this problem again. It's up to you. Do you want to do it on your own right now and I'll just walk around? Or should we just move on to the next problem? Simone, try it real quick? Go ahead. Let's try it real quick. Everybody try this problem out. You're going to solve it the exact same way as the last problem, or different, if that's what you prefer. For instance, maybe you don't like finding slope visually, and you actually want to do the slope formula. That's fine. But either way, your job is to find the slope, and then use point slope form, and then calculate your final answer. Nice notes, Scott. Please put it in. What is that? What's it do? Just look at your pictures.
We forgot that.
I really encourage you, because the material is going to build upon pictures. They're very, very important. Go ahead and draw. At least, you know, we're about to do number 2. Might as well go. Very nice. Good. Good. Hey, nice room about that. That's not right. That looks great. I think everyone in the room got a slope of 3/1, which is really just 3. So there's your slope, and that is population per year. So what does that really represent in units? 3 what? 3 people? Anyone? Yeah, 3,000 people. That's really 3,000 people per 1 year. So that's how the town is growing. They're gaining 3,000 people per year. Presumably through the birth of babies, but not necessarily. People could just be moving to Simonville because it's such a nice place to live. Some of you might be using the 0, 105 coordinate. Some of you might be using the 12, 141 coordinate. By the way, I'm going to do the 0, 105 coordinate because it's a little easier. Yeah, very nice. Looks like many of you are getting 3x plus 105. The interesting thing now is to be able to interpret those units. What does the 3 mean? Now 3,000. And what does the 105 mean? Yeah. Oh, I'm sorry. Yeah, I'm sorry. This isn't just 3,000. It's 3,000 per year, and the starting population was 105,000 people. Yeah, very good. So interpreting this information is very important. All right. Well, very nice. Now keep in mind, these are just, you know, some basic word problems to get us warmed up in terms of reading and interpreting a paragraph, drawing a picture, doing the work. So those 2 good problems. Let's keep going. Now as we go, we might not solve every single one of these. Like if there's duplicate problems, we might end up skipping some of them. All right, so let's take a look at this next one. The mathematical model, C equals 800x plus 80,000, represents the cost in dollars a company has in manufacturing X items during a month. So, folks, first of all, I would go ahead and write it down again. C equals 800 X plus 80,000. What does that formula equal? Like if somebody asked you, it'd be good to be able to say, what does that formula represent? Cost. Yeah, cost. Cost of doing what? Cost to do what? Cost to make how many items?
Cost to
X items.
X
It costs to make X items how frequently?
monthly.
Per month. Right. That's important. That's an important skill right there. It's just be able to take a formula and then describe it to someone else in normal plain English. Oh, that formula, that's the cost to make X items per month. Right? That certainly sounds better than the way they said it. Represents cost in dollars a company has in manufacturing X items per month. Right? You want to reword that in a way that is a little easier. Okay, now based on this, how much does it cost to produce 200 items? Do we find out? Plug it in. You just plug it in. I mean, that's the cost to make X items. I want to know the cost of 200 X. Right? This is really a function, right? C of X. So the cost is a function of X. So we're doing C of 200. That looks a little better. And then you plug in 800 times 200 plus 80,000. And so what is that? 160,000 plus 80,000, which is 240,000. Is that right? Was that problem harder or easier than the last problem? Yeah, a little easier, right? Because all we had to do was plug in a number. You didn't have to come up with a model yourself. They already gave it to us. What does that tell you about word problems? Very easy. Well, some of them are. You never really know just by looking at a paragraph if the problem is going to take a long time or if the problem is going to take a little time. Okay, let's try number 4. A car rental company charges $25 per day to rent a particular type of car and 18 cents per mile. First of all, is that a good deal? Let's find out. Hey, let's find out. Would you pay $25 to rent a car per day? I'm pretty sure my wife and I just did. We just went to Ohio over winter break, and I think the car was $29 a day. Not to say that I got ripped off or anything, but I'd say that's pretty standard. Plus, we got a big minivan because we got a couple of kids. So 25 is probably just a normal car. Okay, so how do we write down our cost function? C of, now it's per day, right? How about instead of X, what letter could we use to represent days? What's it? What, Michelle? D sounds great. So the cost is a function of D, and now it's $25 per day, and then 18 cents per mile. Oh, well, actually, this is a little different. We're going to have to see what they want. This is actually a 2-variable function, isn't it? Because you have the number of days and you have the number of miles. I think maybe, let's just look. One is charged $50.20 for a 1-day rental. So we know for sure that it's just 1 day. So we don't have to use D as a variable because we already know that it's just 1 day. So what's our only variable? Yeah, 18 cents per mile. And in fact, if we just finished reading the question, Juan is charged $50.20 for a 1-day rental. How many miles did he drive? How many miles? We're asking what is M? So we want to know what is M. So now let's write our cost function. Cost in terms of M, since we're doing miles, is the fixed fee of $25 plus the 0.18 per M miles. Yeah? Is that a good function? Okay, so now what do? We figured out our function. Juan is charged $50.20. How many miles did he drive? What do we do with the $50.20?
We plug it into.
Do we? What does M represent?
Miles.
Miles. Is $50.20 miles?
No.
So definitely let's not plug it in. What should we do instead? Yeah, set it equal to. Because this function right here represents cost. And how much did it cost, Juan? $50.20. So we are setting it equal to the $50.20. And now what we're going to do is solve this equation. But folks, let's just keep in mind, whenever you're given a function, and Adon points this out for us, They give you a number. You're either plugging it in or you're setting it equal to, right? Those are your only options. You either plug it into the function or you set it equal to the function. There's really not any other options. So now we go about just solving that. Everybody, you probably need a calculator. So that gives us subtract 25 from both sides. 0.1, 20, and divide by the 0.18. And that gives us 140. 140 what? Miles. That's how far Juan drove. Is that a reasonable amount of miles to drive in one day? What did Juan do that day? Drove to Tucson and back? That'd be more like 200 miles. Who knows? Who knows what Juan did? Maybe he drove to, what's that other place on the way to Tucson? Chandler. No, it's further down there.
Oh,
By the prison?
Maybe not all the way by the prison. Not Eloy. I mean, Eloy's one. What's that other town that's like,
No, there's a high school.
there's a name of it. What is that city? It's not Ahwatukee. Gosh, I don't remember at all, but there is a city on the way to Tucson.
Oh, Marana?
Marana's another one that's really close to Tucson. What's the kind of the big one? Is there? Casa Grande! There we go. Yeah, maybe he just drove to Casa Grande and back. Way to go about that. Okay, so there we go. All done there. Yeah, good takeaway though. With any function, you either plug a number in or you set it equal to. And you can check to know which is which by thinking about the units. Okay. Uh-oh. There we go. Okay, well that was section 1.1. Now we're in section 1.2. Some of these problems will be simple. Some of them might take a little more time. Speaking of time, how much time do we have? We have an hour. Hey, that hour is going to go by like that, folks. Good thing we have an hour left. All right. So find f of 18. What does that mean to do? You just plug it in. Right? I'm not even going to do these ones with you. Okay. What does f of -3 mean? Plug in -3. What does f of 0 mean?
Plug it in.
Plug in 0. Okay. Pretty straightforward. That's just how you use a function. Let's keep going. Write a cost function for the problem. Assume the relationship is linear. Right? We're going to be assuming linearity for a lot of the problems in chapters 1, 2, 17, 3, 4, 5. So a moving firm charges a flat fee of $35 plus $30 per hour. So this company is going to come help you move. No matter what, they're charging you $35, and then they charge you $35 per hour. Sorry, $30 per hour. So let's see if actually the cost of using the moving firm for X hours. So what's our formula? Yeah, 35 plus 30x. Remember, this term is often called the flat fee. The $30 was the flat fee. And then the term with the variable is often called the variable cost, because it's the cost that depends on the variable. And then there's a couple more problems after that. Now let's see, but they get more complex. So let's see what number 9 says. We're still using this relationship from number 8. Or wait, are we? No, we're not. Okay, this is a whole new problem. The fixed cost is $390. So first of all, let's come up with a formula. What would be our general formula for cost? Notice you have a variable term and a constant. Would it be fair to say that every cost formula is going to be of the form mx plus b, where m is the variable cost and b is the flat fee? Does that work? Can we go ahead and just start using mx plus b to represent all these cost and revenue situations?
Yeah.
Yeah. So what do we know then? The fixed cost was $390. So where do I put $390? Yeah, B, that's our flat fixed cost. The flat fee is the same as the fixed fee. Okay, and then it says 10 items cost $58.70 to produce. Well, now, this is tricky. Did they tell us the variable cost?
No.
They did not straight up tell us the variable cost, so I still don't know what it is yet. I'm going to put M. And therefore, so far my formula is C of x equals mx plus 390, but I don't know what M is. What they told us was a coordinate. If we were to draw a picture of this, and a cost function is going to be going up over time, right? This is a general cost function right here. Your flat fee is the y-intercept, And then your variable cost is taking you up, 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 up. And what they just told us was a coordinate on this graph. That's not immediately obvious that they just told us a coordinate on the graph. So we're going to take that in and look at the graph and make the graph yourself. On the one hand, they did tell us the fixed cost. So I can go ahead and know that that number right there is 390. That's my fixed.
Would it be 0, 390?
Yeah, that coordinate is 0, 390. Yeah, absolutely. I'll call that fixed. Was it 390? And yes, that is the coordinate 0, 390. And we also have the coordinate 10, 58, 70. And so now this just reduces to the problems that we've already been solving. Now we're just looking for an equation, and currently we're looking for slope. Do you see a simple way to find slope? We have two coordinates. So you could either do the slope visually, you could do the up, down, right, left. So how far up do we go? Quite a bit, 390 up to 5870. And then how far right do we go? 10. So we can go ahead and find our slope. So m equals, I need a calculator for that.
5,480.
Great, 5,480 over 10. So that's our slope, up 5,480, right 10. That simplifies down to just 548 over 1. Oh, and that's all we need. All we needed now was the slope. We already knew the y-intercept. So now we can say our cost function is 548x plus 390. Now, perhaps you're sitting there thinking, Mr. G, you kind of made a leap in logic there. How did you know that 10 items cost 5870 was a coordinate? Are you wondering that? That's one way they communicate that information. Anytime they give you an input-output relationship, input-output, we're talking about cost after all. So if you input 10 items, you output the cost of 5870, that is an input-output. All coordinates, x, y, are otherwise known as input-output. And so by saying that 10 items cost 5870, they're giving you an input-output information from your cost function, and therefore it's a coordinate. Okie doke. Next one. What's this thing called? Marginal cost. And in fact, at some point on here, we probably want to make a note here about cost. So we have cost equals mx plus b. And we want to know what all of these different terms represent. We already know what b represents. What is b again? B is the fixed or flat cost. Right, so what is m? M, we already said, was the variable cost. There's another word for variable cost, which is incredibly appropriate. M stands for marginal cost. Marginal cost or marginal profit or marginal revenue. I'm not trying to tell you that historically M stands for marginal. I don't think anybody knows why the letter M was used. I've read online, and no one seems to know. But it just so happens that the M can stand for marginal, meaning the marginal cost. That means the cost per item. So let's write down our cost function. C of x is mx plus b. And we now know that the marginal cost is 130, therefore it's 130x. What we don't know now is b. Well, what did they give us? 10 items cost 14,100. What is that information? What is that information right there?
It's a coordinate.
It's a coordinate. That's an input-output relationship. Input 100 items, output 14,100. That's a coordinate. So now we can draw a picture and plug that information in to solve for b. Now, there's actually an easier way, and I want to show you. Other than, drawing a whole picture again. What we know now is that if you input 10, the output should be 14,100. So everybody watch what I'm about to do. If I input 10, watch. If I input 10, which means 130 times 10 plus B,
100.
it should equal, 100, thank you. If I input 100, what should it equal? 14,100. So really look at that. We knew that this 100 items cost 14,100 is a coordinate. And that also means that it's the input-output of a function. So if I input 100, I know that whatever this is, that 130 times 100 plus B, better equal 14,100. And now we can see how to solve for B. Because we can go ahead and just multiply that out. That's 13,000 plus B equals 14,100. And so, solving for B, I subtract 13,000 from both sides. What's B? 1,100? And we did all that work because what is it we're trying to find in all of these problems? To write a cost function. So that means we need our mx plus b. So what's our final answer? C of x equals mx plus b. We knew that our marginal cost was 130. That's the m. And we just solved for b. That was 1,100. So your final answer. What is that, Simone? What? That's a dot.
A dawn. Can you put your thing down?
Oh, yeah.
Thank you.
Oh, okay, what a nice idea.
Is that helpful?
Yeah, thank you.
Awesome. All right, folks. How is everybody? I realize that to a certain extent, this almost feels like boot camp or something, like do push-ups, now do jumping jacks, now do 4 push-ups. Because we're just kind of going through seeing how to solve problems. Hi there. Are you, who's been emailing me?
Yeah.
Okay, do you have a pen? Okay. So folks, go ahead and turn the page and look at the next problem and read it and see what you think. Oh, I'm so glad you're able to come. Sorry for that. Okay, we need this sign right here. I need this. Isn't it? I think so. So you can find everything. Is it in the page? Okay. Alrighty, got this worked out. And see you tomorrow. So folks, you're all going into business in one way or another. So a good question to ask is about linearity. All these problems are assuming linearity. What does that mean to assume linearity? It means that your graph is going to be a linearity means, just in case, so you can all see the etymology of this word, linearity. Linearity. There's the word linearity. Yeah, linearity means that the graph is going to look like a line, and the equation is going to be where it's supposed to be. And so it begs the question, here we are, we're in a business class, we're learning about how to take care of business things in the future, and we're assuming linearity, and every single word problem is linearity. And you're like, geez, wow, this is interesting. It seems like every single problem is linear. So now let me ask you a question. Are there any real life situations in life that are actually going to be linear? I mean, business is a little more messy than that. Supply and demand is a little more messy than that. Really, the real life in terms of supply, demand, and people and humans, not much of that is linear at all. Some things are linear, like when you order supplies from your distributor, that will be linear because you pay so many dollars per product, and so that's linear, yes. But the actual things that we do with supply and demand, those aren't necessarily linear. So why do we use linear models? If things aren't actually linear, why do we use so many linear models? Anyone? Well, that's a good point. Well, yeah, we make it linear, and one reason we make it linear is because linear is easier, right? Linear is easier than a quadratic or a parabola or something like that. So linear is easier, and linear is, ready for it? Close enough, right? Like that's the upshot. That in a lot of contexts, yeah, the real life is a little more messy. It's not linear, but a linear model is often close enough to give you an answer as to what to do with your business without investing all the time and energy and resources that you need to do a quadratic model or a cubic model or something else like that. Okay, so all that said, take a look at number 11. Let the supply and demand functions for a certain model of electric pencil sharpener. Electric pencil sharpener. Who in the room owns an electric pencil sharpener? 0. Do any of you have pencils anymore? We all have mechanical pencils, right? Does anyone have a real pencil? Let's see it. Martha has a real pencil. Do you have an electronic pencil sharpener? You have to, that kind? Yeah. Nice. All right. So none of us can relate to this problem at all, but let the supply and demand functions for a certain model of electric pencil sharpener be given by this. So what are these two models? All right, you've all taken economics classes, I think. So let's just look at this one. What are we looking at here?
Supply.
Yeah, S is supply, right? Very good. And what am I looking at here? Demand. Very good. Q is quantity. Let's keep writing this in. Quantity. And this Q is quantity. What else are we looking at here? P is price. And this P is price. Okay, let's make sure we really understand what this means. Maybe we should finish reading. Where P is the price in dollars. Okay, that's good. It's just dollars. It's not thousands of dollars. It's just dollars. And Q is the quantity and pencil sharpeners in hundreds. Now, you always have to be careful with those units. So that's hundreds of pencil sharpeners, but it's simply dollars. Okay, graph these functions on the same axes. There they are. Graph the supply function as a dashed line and graph the demand function as a solid line. Also find the equilibrium quantity and the equilibrium price. Okay? So let's go ahead and do it. Let's do supply first. How do we graph 2/3 Q? P is equal to 2/3 Q. What's the y-intercept? What's the y-intercept? This is mx plus b. So the y-intercept is 0. So let's graph it. We have y-intercept of 0. So there's our y-intercept. And the slope is up, down, or the right, left? Up 2, right 3, up 2, right 3, up 2, right 3. So here we go. Up 2, right 3. Now notice this is kind of hard to do. It was easy to go up 2 because the axes are in units of 2. It was a little harder to go right 3 because it goes from 2, 4, 6. So you just had to put the 3 in the middle. Now keep going. Up 2, right 3, up 2, up 2, right 3, that brings us to 6. Up 2, right 3, that brings us to 9. Up 2, right 3, that brings us to 12. Up 2, right 3, that brings us to 15. Up 2, right 3, that brings us to... What was that supposed to be? Graph the supply as a dashed line. There we go. Now, one of the cardinal rules of making a graph is to know what you just did. So what does any of that represent? What does Q represent again? Quantity of what? Quantity of what? How many pencil sharpeners? Hundreds of pencil sharpeners. Very good. So this is hundreds of pencil sharpeners. Hundreds of sharpeners. Great. And what does the p-axis represent? Price, which is in what? What unit? Dollars. Just regular dollars. Not hundreds of dollars, not thousands of dollars, just regular old dollars. Okay. So knowing what we just did, let's just pick a coordinate at random and say what it means. Let's choose the coordinate 1612. What does the coordinate 1612 mean? What does the 16 represent? Is that the X or the Y? X. So what does it represent?
1600.
1,600 sharpeners. Very good. So this coordinate represents 1,600 sharpeners. Okay. And what does the 12 represent? X or Y?
Why?
Y, which is dollars. Okay. So there we go. $12, 1,600 sharpeners. Now what does that mean? Does that mean that it cost us $12 to make 1,600 sharpeners? If it did, that's pretty good. To make 1,600 electronic pencil sharpeners for 12 bucks. No. What function did we just graph? We just did the supply curve. Okay, so what does this represent then? That's our supply curve. What does that mean? How many are we supplying?
1600.
We're going to supply 1,600 sharpeners. So us, we are the pencil sharpener producers. We're the manufacturer of electronic pencil sharpeners.
At $12 a piece.
Exactly. I will agree to make 1,600 pencil sharpeners, provided I'm allowed to charge a price of $12. So we better write that down. I, the supplier, right, will make 1,600 sharpeners, provided I can charge $16. No, $12. Okay, that just represents what the supplier is willing to do. So let's immediately ask the question, would you still be willing to make 1,600 sharpeners if you could only charge $1 each? No. No, you're not going to make your money back. Who would do that? What does that $12 represent? That represents how much money you would have to charge in order to make a
Profit.
profit, right? You got to run your business. You got to eat. So $12 is what you figure is the bare minimum that you have to charge to cover all of your expenses, pay your labor, pay your employees, and make a little profit. Okay? So that's what supply really represents, folks. That's a lot of meaning there, isn't it? That's a lot of meaning to unpack and understand so that you can explain it to your employees and to your business partners, etc. Everyone ready to graph the other line? Let's do it. So now we're going to graph the demand curve. D of Q equals, now notice it says 15 minus 2/3 Q. I'm going to write that backwards as negative 2/3 Q plus 15. Why did I write it backwards? Because we're using a linear model, which is mx plus b. Yes.
MX plus B.
Because this is mx plus b right there, right? You all recognize it as mx plus b? It's negative 2/3 Q plus 15, but it is nevertheless mx plus b. So we write it so that the x term is first, followed by the b term. Okay, so now we need to draw that. Where's our y-intercept? 15. So we put a dot on the y-axis at 15. And now our slope is negative 2/3. Where do we put the negative sign? I always put the negative sign on top. I just like to. So what's the up, down of the left, right? Down 2. Right 3. Down 2, right 3. Down 2, right 3. Down 2, right 3. So let's do it. Down 2, right 3. So we go down 2, right 3. What does it start to do? Just know that your dots are going to be right on top of the other dots because we're still going right 3. So down 2, right 3. Down 2, right 3. Oh, there's our point of intersection. The point of intersection happened to land right on top of it. Color it for it. And then we'll continue going down 2, gosh, down 2, right 3, and down 2, right 3. Okay, good enough. Okay, and how are we supposed to graph this one? Graph functions on the same axes. The demand function is a solid line. So here's my demand function. Now what you're doing right now, drawing this graph is like the most important thing, or probably the most important part of this class, is how to take this information and represent it graphically. Okay, so now what? Let's just go ahead and choose a point and make sure we understand what it means. So let's choose this point. How about this one right here? What's that coordinate? Is that the coordinate 18? Is it 18.3? I think that's the coordinate 18.3. We can all pretend it in case. It's the coordinate 18.3. No, it's 5. I'm way off. Hold on. I want to make sure that we're doing this right. 18 divided by 3. 6 times. Oh, it is 3. Okay, 18.3. So let's take a look at that one. What does that mean? What does the coordinate 18.3 mean? What's the first number represent? X or Y? Single. X or Y?
Isn't it, yeah, X,
X. And the x-axis represents?
the hundreds of like,
Yep, so that's 1,800 sharpeners.
So for 1,800 sharpeners, we'll charge $3 a piece.
Well, let's think carefully about that. The 3 is the Y coordinate, which is dollars. But right now, we're talking about the demand function. So what does demand represent?
What they're asking for.
Supply is the business that's manufacturing the items. That's the supplier, the business. Who's demand?
Us.
Us, the consumer, right? Demand is the consumer. Supply is the business. So what are we really saying here then? As a consumer, or as all consumers, okay, in this town, all consumers in the world, if you charge $3 for an electronic pencil sharpener, how many of us will show up to buy it? 1,800 of us. That's what this says. So if this company only charges $3, 1,800 of us will be willing to go buy a pencil sharpener. And if you raise that pencil sharpener price to $4, forget it. A whole bunch of us aren't going to buy it. Maybe only 1,200 of us will buy your stupid pencil sharpener. So that's what that part represents. So again, in words, we, the consumers, will buy 1,800 sharpeners if you charge $3. Or maybe it sounds better if you say, if we only have to pay. Yep. So at this point, is there a lot of agreement between the supplier and the consumers? Yeah, we're pretty off right here. The suppliers are wanting to charge $12, and the people are only willing to pay $3, right? So where do we find agreement? Where do we find agreement between supplier and consumer so that they're both willing to sell it and buy it at the same price value? What special point is that?
Equilibrium.
That's what the equilibrium quantity represents, right here. So everybody label this point right here. The point of intersection is the equilibrium. So that point of intersection right there, point of intersection, is the equilibrium. And that's the last part of this question. It says, do all this graphing. We just did it. We just did all this graphing. We interpreted it. We know what it means. Now find the equilibrium quantity and the equilibrium price. Well, the equilibrium point, okay, this point of intersection, x, y, is the equilibrium quantity and the equilibrium price, right? Because x represents quantity and y represents price. So all we need to know is that point of intersection, and that is the equilibrium. So everyone just look at your own graph. What's the point of equilibrium?
12.8.
12.8. So what does that mean? What does 12.8 mean? Let's write it down. This is going to be my final answer. Equilibrium. That's x, y. That's quantity price. So how do we interpret that? 12 what? 12 is quantity, so
1,200
1,200 sharpeners will be bought and sold.
at $8.
Yep, at 8, which is dollars, $8 a piece. Okay, so we just found out something really good and interesting. In this society, where this business is operating with these consumers, if the business will just make 1,200 pencil sharpeners, they'll be willing to sell them at $8 a piece, and consumers will be willing to buy them for $8 a piece. And what will happen to all 1,200 of those sharpeners? They'll be sold, right? Isn't that ideal? Because does a business want to have overstock? No, they don't want to have 1,000 sharpeners sitting on the shelves gathering dust. And does a business want to sell out with customers banging on the door, wanting more? That's bad publicity, right? Oh, they ran out. Oh, I don't want to shop with them anymore. They run out all the time. They never have my product. I'm going to go shop somewhere else. What's that?
Is the answer key correct?
Well, I don't know. What does the answer key say?
The delivering quantity is 1125 and then the price is 750.
Well, folks, I have to tell you, we were merely looking at this graph. Maybe, what did you say the answer was?
1125 for the quantity
Uh-huh.
and then 750 for the price.
Oh, boy. So, folks, you can see that our numbers are awfully close, right? Let's see that. Now, I think we just learned a very valuable life lesson. Where did we get the number 12.8? By looking at the graph. Or is our graph perfect?
No.
No. So now how do we get the exact answer? We definitely got a very nice approximate answer, and it was worth getting because we saw how to draw a good picture and how to interpret it. But now how do we actually find out where the point of intersection is? Well, you could graph it on your graphing calculator and use your graphing calculator to find out. But what we want to know is, this point of intersection is the point where both of these functions have the same height. Remember, f of x represents height. And if we want both of these functions to have the same height, which is what happens right here, not here, because here this is taller and that's shorter. Here this is taller, that's shorter. We want this one right there with the same height. That means you just have to set the two functions equal to each other. So make a note to yourself here to find point of intersection, which is really just solving a system. Set the functions equal to each other. Okie dokie. So let's do it. We're going to set S of Q. I better go somewhere else. I hope that I realize you might be running out of room too. I'm running out of room. So set S of Q equal to D of Q. Now this is a good lesson right here. That's the definition of finding the equilibrium point. So in a economical supply-demand problem, you find the equilibrium quantity by setting supply equal to demand. After all, isn't that what we're saying? This is the point where supply is equal to demand. So let's set those equal to each other, and that will be 2/3 Q must be equal to 15 minus 2/3 Q. Now let's solve. Oops. 2/3 Q. So we want all of our variables to the left. So I'm going to go ahead and move this 2/3 Q over to the right. Sorry, over to the left. That gives us 4/3 Q equals 15. Now how do we solve for Q? Q is being multiplied by 4/3. You multiply by the reciprocal. That's the most efficient way. If your variable is being multiplied by a fraction, just multiply by the reciprocal of that fraction. So I'm going to multiply by 3/4 on both sides. And so they cancel out, and you get Q is equal to 15 times 3/4, which is 11.25, which is the answer key answer. 11.25 is the quantity, which is what Josue said, which is awfully close to 12, which is what we thought it was just from looking at the graph. Okay, so now how do we find the price? Now we know the quantity. How do we know the price? That is the height. Remember, price is height. How do we find height? You just plug it into which function? Do you plug that value, 11.25, into this one or this one? Which one do you plug it into?
The one we put together.
Either one.
Either one.
Remember, either one, because at this point, they have the same value. They have the same height. So you plug it into either one, and I'd say this one's easier. So I'm going to plug it into this one. So now I take my Q, equals 11.25. I'm going to plug it into my supply. So S of Q equals 2/3 Q, which is going to be S of 11.25 which is 2/3 7.5. Host Way, I sure am glad you checked the answer key on that one.
Just because my graph was off, so that's the only reason I checked.
Yeah, you know, I just was a little, that's what do you call that? A little confident in my graphing skills there, right? Like, it's really important to make a graph, but it's also very important to verify your work through algebra. So this is how you find the equilibrium point of a supply and demand problem. You just set supply equal to demand, solve for Q, and then plug Q back into either function, and that will tell you the dollar value. Now, folks, just looking at all of your faces, do any of you feel like, oh my gosh, that was a long problem? What's that, Adam? Yeah. Yeah. What'd you say, David? What'd you say?
That was an easy problem. It was just like the explanation and everything.
Well, that's true. The explanation was a little long. What's that? What were you saying? A little long. But you're right, because we were explaining a lot. We were making sure that everybody's on board, that we all know how to interpret supply and demand problems. If we had another problem just like it, do you think we could get the answer like in a minute? Mm-hmm. Probably, because we wouldn't have to bother with all the explanation. So let's go ahead and see what the next question is. Oops. Oh, no. Do not leave.
So I mean, it's time to go.
No, see, I knew it. I knew it. Ha, ha, ha. Okay. There, that was the one we just did. Okay, now we're here. Okay, great. Now, number 12, we should be able to do this one much faster. Because now we know what we're talking about and what we're doing. Boy, I'm going to rip that plug right out of the wall one of these days. Why would anyone put a plug right where people stand? But folks, your graphs are beautiful. That's what this is all about. I mean, you know that, right? Like if you went to a business meeting and you didn't have some sort of like a big poster projector with like a graph on it, like isn't that like the stereotype of what people do at business meetings? They look at graphs. It's really important. Okay, let's take a look. Suppose that the demand and price for a certain model of graphing calculator are related by this demand function. So this is merely the demand function, where P is the price and Q is the demand. Find the price if the demand is 200. Oh, well, this is a much easier problem. That's just the function. Find the price if the demand is 200. What do we do with the 200? Do we plug it in or do we set it equal to? I hear plug it in. How do you know that we're plugging it in?
Guessing.
All right, thank you for your honesty. What do we do? Because remember, it's always you either plug it in or you set it equal to. What type of number do you plug in? A quantity. What type of number is it equal to? A price, which is a dollar value. What is 200 calculators? Is that a quantity or a price?
Quantity.
It's a quantity. So are we going to plug it in or set it equal to?
Plug it in.
We're going to plug it in, right? So you use the unit of the problem to convince yourself which one you're about to do. So our formula is D of Q equals 108 minus 3.25Q. And we want to use the 200 by either plugging it in or setting it equal to. Q, we're going to plug it in. That's appropriate because 200 calculators is a quantity. So we do D of 200 equals 108 minus 3.25Q. Did we just do that right? I don't think so. Because if you calculate that out, like I'm about to calculate that out, what are you going to get? You get a negative number, don't you? And can price be negative?
No.
So what do we do wrong?
Should be 2.
Right, it should be 2. Because look, Q is the demand in hundreds. So if the demand is 200 calculators, we represent demand by simply the number 2. So we're really just plugging in 2. What does this tell us? That the textbook authors hate us? No, it just means we have to be careful. It just means we have to be careful. So if we plug in 2, now that's 108 minus 650, which is simply 101.5, which is the price. Notice that how convenient that was that they left that P equals in front of the whole formula. It's as though they wanted to remind us when we were all done that D of 2, once you're done plugging it in, the 101.5 is the price. And is that thousands of dollars? Just dollars. It says P is the price of dollars. So how do you interpret that? If the demand is 200 calculators, the price is 101.5. So what that means is, if a company charges $101.50 for a graphing calculator, how many people will show up to buy it? 200. No more. No less. If you charge $101.5 for a graphing calculator, 200 people will come out of their homes, come to the store, buy that graphing calculator. That's what these models represent. They represent the mind of God. They're saying this is what will happen. If you charge $101 calculators. Doesn't that sound crazy that that's what a supply and demand model really represents? It's trying to tell the future. That's what a supply and demand model represents. It's trying to tell the future. Okay, one more. A book publisher found that the cost to produce 1,000 calculus textbooks, everyone's favorite, is $25,300. So that's how much it costs to produce all 1,000 textbooks. While the cost to produce 2,000 textbooks is $51,000. Notice that seems fairly reasonable. You doubled the amount of textbooks, and you doubled the cost. So that seems reasonable. Assume that the cost C of x is a linear function and a number of textbooks produced. What is the marginal cost? Who remembers what part of the formula marginal cost is? The m, and mx plus b. Exactly right. So what are we doing here? We need to find a cost function. And at the end of the problem, they want to know what m is. So what have they told us so far? What is this information right here? I'm looking for a one-word answer that starts with the letter C. When they tell us that it's 1,000 calculus textbooks cost $25,300, that information is a coordinate. That information is a coordinate. What's this information? That 2,000 textbooks cost $51,100. That's a coordinate. So we need to come up with a graph, and we have to label our axes correctly. So what are our axes? Cost, C of x, is always the y, right? The function is always the y. F of x is the height. That's the y value. So our cost is the y-axis. What's our x-axis? C of x is the cost, a function of x, the number of textbooks. What does x represent? Number of textbooks, which is quantity. Notice, folks, that even just the decision to know which one to put where takes a little bit of mental effort. Now, to be fair, dollars almost always goes on the y-axis. Dollars is almost always the y-axis. But to be fair, you have to think it through and make sure. So now what do? Now that we have that, we can put our 1,000 textbooks was 25,300. That's one coordinate. And now our 2,000 textbooks is 51,100. And that's that coordinate. And there's our line. And away we go. And we're not going to solve the rest of that problem. Because we've solved this problem already, haven't we? We've solved one just like it. So you find the slope, and in fact, as soon as you're done finding the slope, that's all you need. The question doesn't say find the equation of the line. That would take more effort. All the question says is, what's the marginal cost? And what is the marginal cost? The slope. The marginal cost is the slope. And in fact, we will finish this problem, because do we already know the slope? Just look at the graph. Do we know the slope? Up, down, right, left. What's our slope? The slope is up 24,800, right, 1,000. Did I subtract that correctly, anybody? I hope so. And then that becomes 24.8 over 1. What is the cost per textbook? Remember, the y value was dollars. The x value was textbooks. So what does this number represent?
It's 25,800.
Sorry?
25,000.
Oh, was I wrong? It's 25,000? Thank you, Josue, for checking it. 25,000, 25.8. There we go. Okay, so what does our answer represent? Yeah, it costs $25.80 to make one textbook. And that is the question. What is the marginal cost of a calculus textbook? The marginal cost is, what is the cost for one textbook? The cost of one textbook is $25.80. Yep. Boy, aren't word problems fun? What's the hardest part about a word problem? And don't say staying awake.
The words.
The what?
The words.
The words? Comprehending?
Just breaking it down and get what you need.
Breaking it down? Yeah. I admit it's tricky. I'm in a math class right now, and I was doing my homework last night. I got to the very last problem, couldn't figure it out. So I said, I'm just gonna go to bed. And since I just went to bed, and since yesterday I've just kind of thought in my subconscious brain, I think I almost have it figured out. But the point is, sometimes you need to spend time with it, right? You know, it doesn't come obviously, so you spend a little time. Okay. What do we have left? 14 through, 3 more word problems. You know what happens if we finish early?
We get to start the second part.
Exactly. You jokesters. All right. Good response, Adam. All right, let's do it. Everyone go ahead and read this next problem and do it on your own. And by that I mean, you know, try to suss it out. Read through it, see what sense you can make of it. Try to write down as much as you can. Make a graph. Label your axes. See if they gave you any coordinates. If they did give you a coordinate, label it. See what you can do. The goal, now let me just tell you folks, I'll be honest with you. The goal when you start a word problem is not to solve it. The goal is to write down as much as you can. Because if you can write down as much as you can, you know what happens sometimes? The answer just falls out. You're like, jeez, I just kept writing things down, and before I knew it, I had the answer. Right? So the goal is write down as much as you can. So everybody give it a shot. Write down as much as you can. I'm serious. Sometimes writing down the function is a great way to start. Very nice, you wrote down the formula, that's great. Very nice, and you wrote the formula and function and you started the graph. Well done. You wrote down the formula and the function, underlining. Very good, got your functions, equations, very good. Nice bypass, starting to drive your friend. All right, folks, let's compare notes. I know that wasn't enough time to solve the whole problem, and I know that you're all in the middle of working through the problem. First of all, I just want to compliment all of you. That was wonderful. Just walking around, this is what I saw. And it was a big smiley face because it was beautiful. It was wonderful. Like seeing the things you're doing. I saw some underlying, I saw some highlighting. I saw people writing down the formula mx plus b. I saw some people writing down the cost function. And I saw people starting to rank their graphs and their axes and even labeling some coordinates. So that's wonderful. That's the name of the game. When you start a word problem, the goal is write down as much as you can. And don't stop. And don't cross it out. I saw just one of you cross something out. You never know, you could have been right. So don't cross it out because that could be a valuable idea. Okay, so let's see what we have here. Toilet manufacturers decided to come out with a new and improved toilet. I don't know how you make a toilet better, but they are doing it. The fixed cost for the production of this new toilet was, so here's our cost function, right? So the cost is 16,600 and the variable cost of 66x. So I think a lot of you had that. That's our cost function. Now notice the next thing they tell us is the company expects to sell the toilets for $156 each, which is very reasonable. I mean, kitchen faucets cost $150. So a whole toilet for $150? What a deal. So what does that represent? If they're selling it for $156, that's revenue. So let's make a revenue formula. Revenue means how much money are you going to make per toilet? Like if it costs $66 per toilet, we're going to charge $156 per toilet. What do I write down? 156x. So everyone take a moment, write that down. That's your revenue function. And make sure that makes sense to you, right? Because let's just do an example. R of x equals 156x. What if I sell one toilet? How much money did I just make? $156. $156, right? What if I sell two toilets? How much money did I just make? Yeah, $312. So that's a very reasonable function to be our revenue function, right? Okay, so far so good. Formulate a function p of x, what does that represent?
Price.
Very tricky. This one was profit. In the previous problems, lowercase p represented price, uppercase p represents profit. Is that fair or kind? No, but it's reality. So lowercase p is price, uppercase p is profit. Likewise, uppercase R is revenue, uppercase C is cost. So what is profit? Generally speaking, the formula, the concept. Profit is the difference between revenue and cost, right? You take in all the money from your revenue and you subtract out all of your costs, and that's your profit. So the formula for profit is revenue minus cost. Very important formula. You should all memorize it off the top of your head. Profit is revenue minus cost, which makes sense. You know, all the money you take in, take away all the money that you spent, that's your profit. Okay, so now what? It says formulate a function p of x for the total profit from the production and sale of x toilets. So this is what we want, right? We just want p of x. And do we know r of x? Yeah, it's 156x. And do we know c of x? Yeah. So we just have to write it down. So that's 156x minus, now be very careful here, our cost function is a two expression, well, it's got two pieces. So you have to use a parenthesis to say 16,600 plus 66x. That's our profit. So what do we do with this minus sign? We have to distribute. So we end up with negative, well, it's going to be 156x minus 16,600 minus 66x. So 156x minus 66x is what, 90x? Minus 16,600. Did anyone else get that? Okay. Now I realize this problem was very different from all the problems we did previously. Did we have to draw a picture for this? No. We didn't. At no point did it really call upon us to make a graph. I mean, we could have made a graph of the cost function. We very well could have. We could have started to think, okay, cost, this is how many toilets we're selling. This is the cost of the toilets, which is dollars. And then we could have said that the fixed value is 16,600. And then we know that we're charging more and more and more as time goes on. So you could have drawn a little graph of the cost function, you know, and just make sure it makes sense. I mean, should cost go up the more products you sell? Yeah. So that would be your cost function, but we just didn't need to. Okay, does that feel like a letdown? We didn't end up doing all that much. We just came up with a formula for profit. Okay, let's keep going. Regrind. I have no idea what that means. Regrind Incorporated regrinds used typewriter platens. Anyone know what that sentence just said? Anyone?
No.
Is it important that we know what it said? I don't know. Should we know what that says? Should we understand what we're reading? Typewriter platens. Aha! A typewriter platen. Of course. What is that thing? Where is the typewriter platen within a typewriter? Hold on, I don't want to go to eBay. I want to go to Google Images. There we go. What is the typewriter platen? Do you all see it? It's the rolling bar that the paper rolls over as you type onto it with your typewriter. Folks, this is a very important word problem, right? Which company is doing this? Which company, Regrind Incorporated, regrinds used typewriter platens? What do you suppose that means? Yeah, they renew them. They make the typewriter platen new again so that you can buy it used and get a new one. Because are they still manufacturing typewriters? No. Are there any companies making new typewriter platens? Probably not, because there's no demand for typewriters. So, but there is still a demand for people who have typewriters, and their only option to get a platen now. Typewriter platens. Okay, the cost per platen is $1.30. So that's how much it costs them to regrind it and make it new again. The fixed cost to run the grinding machine is $352 a day. So what's our cost function? Per day, the cost is?
352.
352 plus?
$1.30.
1.3x. Everyone feel good about that? That's the cost for Regrind Incorporated to run their business. If the company sells the regrind platens for $5.30, now what is that telling us? They're selling it for $5.30 each. Now are we talking about cost or are we talking about
Revenue.
revenue? So now our revenue is 5.3x. So there's a revenue. Now they're saying, how money must be reground daily to break even? What does break even mean?
Just make your money back that you spent.
Right. How much profit are you making if you break even?
0.
0. So that means that P of x, which is R of x, minus C of x, should be equal to 0. So we want to solve this equation for x. We want to say, which x value would I have to plug in for profit that would make that whole thing equal exactly 0? So here we go. Revenue is 5.3x minus 352 plus 1.3x, which gives us 4x minus 352 equals 0. Because that's our profit function, and we want to know when is profit 0? That is, when are we breaking even? So how do we solve for x?
Bring the 352 over.
Yeah, do algebra, right? So 4x equals 352, divide by 4, what do we get? 4 goes into 352. 88. 88? Great. 88 it is. So if they regrind 88 platens a day, how much money do they make in profit? None. Right. But if they make 89, or if they regrind 89 platens a day, they just made some profit. But if they only regrind 88 platens a day, they didn't make any profit at all. And myself personally, I can't even imagine sitting down to regrind 88 platens a day. That sounds mind-numbing work. I would have to watch Netflix.
Just to get your money back.
Right, I know, that's just to break even, right? 88 regrinds. Whew. Okay. Very nice, folks. You all just heard my phone go off. That means we have 5 minutes, and we have one problem left. Talk about timing. After we finish this problem, I'll let you all go. Not early, just I'll let it happen. This is great. By the way, we've covered really good information today, folks. A lot of concept. Concept is so important. We covered cost, revenue, profit, break even, supply, demand, graphing. It's a good day. A lumber yard, what is that? No, I'm serious. Anybody? Lumber? Anybody? Lumber yard? What is lumber? Wood. It is wood. Exactly right. Perhaps you've passed Paul Bunyan's firewood shop or a lumber yard. Let's just look. Lumber yard. There it is. It's a big old place with lots of wood. Right? A lumber yard has fixed costs of $4,692 a day and variable costs of $1 per board foot produced. Okay? So let's just write that down real quick. The cost is $4,692 and a variable cost of $1 per board foot. What are we producing? Board feet. What does that mean? Typically when you buy a piece of wood, how long is it? Like pretty long. Right? Like let's say that you're buying a piece of wood that's 6 feet long. Every board foot is 1 foot of that board. So you're buying the cost is in terms of feet of board. That's what a board foot is. So if you bought a piece of wood that the whole thing was 6 feet long, then this is 6 board feet. Because you break it down into each foot. There's a board foot, 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 there's a board foot. All right, so they're talking about how many board feet of lumber they're making per day. The company gets $2.50 per board foot sold. Now what are we talking about? Revenue. So our revenue is $250 per board foot. Remember, X represents board feet. And then what? How many board feet must be produced to break even? So it's a similar question. We're saying we want profit, which is R of X minus C of X, to equal 0. I have this fantastic thought in my head that like, I say, okay, everyone, go and solve that problem. And then I just pack up and sneak out. So you guys are all still here. That's just a little joke, folks. I would never do that to you. But it's awesome.
Like you say, I'm going to the bathroom and there's no.
Anyone have the answer they want to share?
128.
128 board feet? Was it really?
3,128.
3,128. Is that what anyone else got? 3,128. That's how many board feet you have to make out of pure pieces of wood in order to break even.